Hello everyone. In this video we are going to discuss about power factor correction. Right? Power factor correction is made possible using a suitable value of capacitor. Here on your screen you can see some capacitors which are small in nanofarad or microfarad, and these are actually for small circuits. But we have also a capacitor bank for the power system, which is used for power factor correction in a large power scale. Our companies charge more for larger current because of low power factor results in increase in power loss by a squared factor, since P is equal to I squared R. So therefore, since you can see here the power loss is I squared R. So I is, if your I is very high and you square it, you will have a large power loss. So it is beneficial for power company and the consumer that every effort is made to minimize the current level or to keep the power factor close to unity as possible. So the solution is to choose a suitable size of capacitor, and the current can be made completely in phase with the voltage source, implying a unity power factor. What really happens in the power system is that from the power plant toward the customer, there is a very long distance transmission line, right? If your current is high, so the power loss will be dissipated equal to I squared R, right? I squared R. R is the resistance of the transmission line. So I squared R is the power loss in the system. So if your power, again as I said, if I is very large and you square it, we will have a large amount of power loss in the transmission line. So the objective of power factor correction is to reduce the current so that the power loss will be reduced also. But the question is, what is the value of the suitable capacitor for your power system to make it unity power factor? So we need to have a basis for that. Also, let me discuss to you the unwanted effects of the of industry operating at low power factor. Number one, the intensity of the current flowing in the distribution lines supplying the power to the industrial application increases, right? So the intensity of the current increases. Of course, if we have a large amount of current, we need to increase the size of the conductor or the distribution lines. So if we have a large current, we have to increase the cable. So it will cost some amount to the power company. And it will also affect the weight of the transmission line, so the structure also of the tower must be considered. Also, the amount of copper loss, as I've said earlier, I squared R. So the copper loss in the line is also increased, and also the voltage at the main power bus of the industrial application decreases, right? There will be also the difference between no load voltage and the full load voltage, so the difference between them is large. So the voltage of the main power bus decreases. The amount also of active power supplied to the industrial application also decreases. Now, there are some methods in doing power factor correction in the plant, right? It can be a plant-wide power factor correction. What does it mean? As you can say, consider this as your power plant, as your factory. This is the factory load, and the main capacitor bank is being installed close to where the power source is located. So we have the power bank here, right? That means to say all the loads that is connected to this in parallel with this capacitor bank, the power factor, the lagging power factor is to be corrected by this capacitor bank, right? There's a controller on this capacitor bank. This controller constantly monitors the reactive power demand on the industry application and switches capacitor in and out in order to supply the proper amount of reactive power required, right? Such controller enables the power factor of the industrial application to be maintained as close to unity. So there is an automatic switching here, whether to add capacitor or not, depending on the type of load that is connected. If you have a large inductive load, that means your power factor will be very, very poor, so your capacitor bank will adjust automatically. This is called a plant-wide power factor correction. There is also another method wherein they install the capacitor in parallel with each equipment. They install the capacitor for each equipment. But this type of power factor correction can only be used when the reactive demand of each inductive load does not vary much over time. So we have almost a fixed load on each equipment. So this is what you call distributed power factor correction. So each capacitor is being distributed to its load in the factory. Now, in the house, most domestic loads such as washing machine, air conditioner, refrigerator, and also some induction motors are inductive and operate at low lagging power factor. Although inductive in nature, the load cannot be changed. We can increase the power factor by selecting a suitable rating of capacitor to be connected in parallel. So this is our load here. With the low power factor, all we need to do is to put a capacitor in parallel with the load, also parallel with the source, in order to correct the power factor of the current with respect to the voltage source. So what are the expected values of power factor? The expected values of power factor is from 0 to 1. 0 to 1. 0 is a unity power factor, since power factor is equal to cosine of the phase angle between the voltage and the current. As you can see, this is the waveform of the voltage, and this is the waveform of the current. The phase angle between them, which is this one, is the cosine of this phase angle is the power factor. So the value is from 0 to 1. Okay? So now, if the load circuit behavior is inductive, the power factor is lagging. If the load circuit behavior is capacitive, the power factor is leading. So, if theta B minus theta is equal to the phase angle between apparent power and the real power. So when we talk about, this is when we talk about the power triangle, which I'm going to discuss later. So from this waveform here, you can see that the current is lagging the voltage by some angle phi. Right? This angle phi represented in phasor as B is the reference, angle 0, and IL is a current with a certain angle with respect to the reference. So this is current is lagging. So what is power factor correction? The process of increasing the power factor without altering the voltage or current of the original load is known as power factor correction. The main objective of power factor correction is to adjust the power factor of the load close to unity, or even exactly equal to unity. Now, in order to what? To save energy, reduce the losses, we can save money that we pay to the power company. Another advantage of power factor correction is the power generating plant will be more efficient, thereby consuming less fuel for fuel type engine generator. Now, what will happen if we just select randomly a capacitor without having some calculations? Suppose this is the existing power factor of the system, 0.5 lagging, right? 0.5 lagging. I mentioned here lagging, that means this phasor represents an inductive load, right? So, now if we put a power factor randomly without calculation, maybe after we put the capacitor without calculation, we had improved the power factor, but it's still not enough. Just like here, only 0.7. Still, 0.7 lagging still is not a good power factor. Now, or otherwise, if we oversize the capacitor, we will have a leading current. Let's say, for example, 0.5 leading power factor, which is also not practical, and it's also you cannot save power, or you cannot save money that you pay to the power company if you have oversized the capacitor. So if that is the case, we need to determine what is the the size or the capacity of the capacitor that we are going to connect to the system. But before we do that, let us be familiar with the different type of power. So we have real power, the power which is what? Actually consumed or utilized in an AC circuit. This is also called true power or active power or real power. Now to determine the formula to determine the real power is equal to 1/2 B max I max cosine theta B minus theta I. So 1/2 B max, so this is BS in terms of B peak or B max I max multiplied by the cosine angle between BS and IL. So this is one equation. Or otherwise, in terms of BRMS, we have power is equal to BRMS times IRMS cosine theta B minus theta I. So we all know that B max is equal to square root of 2 multiplied by BRMS. So if we solve for BRMS, we have B max over square root of 2. Okay? So now, also another equation is power is equal to IRMS squared, the square of the current, multiplied by the resistance is equal to BRMS squared over R equivalent, right? So we have two formula here. This is in terms of current, IRMS squared times REQ, or BRMS squared over REQ. Now, let us check about the power triangle. From this power triangle, we show you that when we have a lagging power factor, we have, this is our real power, which is our reference, and this Q here, we have a positive Q. The Q is positive, meaning it is on the top of the phasor, the reference phasor. This is positive Q. So when Q is positive, our load is inductive. Again, when Q is positive, our load is inductive. And this one is the apparent power. Okay, later I will show you what's the relationship between Q and S. If we have a negative, if Q is negative, we have a leading power factor. So if it is leading, we have a capacitive load. And here, we have an inductive load. Okay? So, again, from this part, it's also from power triangle. In this case, S is equal to P. We have a power factor equal to 1. Or we have a unity power factor. Right? So, the next type of power is a reactive power, which is QL, QC. The power which flows back and forth, that means it moves in both the direction in the circuit or react upon it. It is called reactive power, or the units are VAR, or volt ampere reactive, or kilovolt ampere reactive, or megavolt ampere reactive. Right? Bar means volt ampere reactive. So, for an inductive load, QL is equal to BRMS times IRMS sine theta B minus theta IL. Or QL is equal to 1/2 BMIM sine theta B minus theta IL. Or we can calculate QL is equal to BLIL, or it means to say, what is BLIL? It means to say that if we have the voltage across the inductor, this is the inductor, this is the resistor, this is the capacitor, if they are together, BL here is the voltage across the capacitor. This is the B source, right? The B source is connected here from the source. So BL is BLIL, or I squared. Of course, here we have this current. This is IL. This is IL. Okay. This is the, or QL is BLIL is equal to IL squared XL and BL squared XL. This is for the inductive load. For capacitive load, it's called BCIC times I squared C X of C, or equal to B squared C X of C. Or we can use the BRMS, IRMS sine theta B minus theta I. So the value, this one will change depending on the theta of the source, the voltage across the source, the voltage across the capacitor, and the current on the capacitor itself, right? So QC is 1/2 Bm Im sine theta B minus theta I. So this is the formula for, so we have two types of power here, real power and reactor power. So since we talked about earlier on the power triangle, so we have real power, reactive power. We also have what you call apparent power. As you can see, it is a triangle, so we can apply the Pythagorean theorem here, right? So if we can apply the Pythagorean theorem here, we can also say that the power factor is the cosine theta B minus theta I. It's also equal to the real power P over S, right? This is the cosine part. P over S is the power factor. So now another type of power is the apparent power, the product root. The product of root mean square, RMS value of voltage, and the current is the apparent power. It's measured in VA, kVA, or mega VA. S is equal to BRMS, IRMS, the source, right? And 1/2 Bm Im, or S is equal to P squared plus Q minus QC squared, right? From where did I get this QC minus QL? If I have here, this is Q, let's say this is QC, and QL, I have here a QC here, QC. So this QC will be subtracted from here. So let's say here, this is the QC, which is going down, right? So here now, here is our S, or this one. Or in this case, from this figure, it means that this Q here, the Q here is equal to QL minus QC, right? So it means this is the power triangle of a given circuit. Now, Q is positive, power factor is lagging. When Q is negative, power factor is leading. Now from here, if we talk about, again, what will be the Q here? We have an inductive load, so Q is positive. This is P, the P dissipated on this resistor, and S, that the total S is equal to V times I, right? So it's this voltage times this is the total power. So now, what is P from this power triangle? P is equal to S1 cosine theta 1, right? Cosine theta 1. P is equal to S1 cosine theta 1. Q1 is equal to S1 sine theta, theta 1. Or Q1 is equal to P tangent theta 1. Q1 is equal to P tangent theta 1, right? Because tangent, right, as tangent is equal to y over x, right? This one is y, this is x. So tangent, so we have, so we solve for y. Y is equal to x tangent theta, right? Let's say tangent theta. Okay. Now, let us derive the equation to find the value of C that we need to put in parallel with the load to improve the power factor from theta 1 to theta 2. So let's say our objective for theta 2 is unity, right? Unity. Okay. So this is our figure. We have this circuit, an inductive. So what's the relationship between the voltage and current? The current is lagging because we have an inductive load. So when I draw it in phasor, this is the B angle 0, and this is IL with an angle of theta 1, right? Now, if I'm going to put a capacitor here, earlier here, we can say that the current I is equal to IL, right? The current I is equal to IL. Now, if I'm going to put a capacitor in parallel on the next circuit, right? Let's erase the. Okay, so I put. Now we can say that the current I. Let's call the I now directly from the source as I prime. I prime is equal to the vector summation of IL, which is this one, plus the vector IC. So, since it is a vector, we can represent it by a phasor. So, originally, we have this as theta 1. When we put IC in parallel with B, right? In parallel with the source, this will be the phasor of the current. So, this current is reflected here by phasor graphical phasor representation. So this will subtract here. So that means to say the total current here, let's say I will call it I prime. I prime is shorter than IL, right? The original IL. So what does it mean? We had reduced the, when we put a capacitor, we reduce the I. So it becomes I prime now. So what happened to the theta? Theta also become very close to, we have here, close to the source, right? It becomes almost in phase with the source. Okay, when we put the capacitor. So notice also here, but what is the value of C? What is the value of C in parallel? From for C, we can calculate the power or the reactive power across C as Q sub C is equal to Vrms squared X of C, where X of C is equal to 1 over omega C, right? So X of C is equal to 1 over omega C. So solving for QC, we will have QC is equal to omega C Vrms squared, right? Now let's check about power triangle. From power triangle, we have QC. We have QC is equal to Q1 minus 2 Q2. QC is the power on the capacitor, which is equal to this. QC is equal to Q1 minus Q2. And Q1 is P tangent theta 1, P tangent theta 1, and Q2 is P tangent theta 2. Right? Factor out P, we have QC is equal to P tangent theta 1 minus tangent theta 2. Since this is QC and this is also QC, we can equate these two equations to solve for C. Omega C Vrms squared C is equal to P tangent theta 1 minus theta 2. Solving for C, we will obtain P tangent theta 1 minus theta 2 over omega Vrms squared. So this omega is actually 2 pi multiplied by F because the capacitor is dependent on the frequency. Now, after we do the calculation, we determine the capacitor. We can now decide what are the capacitor needed to correct this, the low power factor in order to reduce the losses on the line, right? So initially, current IS is high, and the generated kVA of the power plant here will also be high. But if we put a capacitor on each client, on each customer, they corrected their capacitor, the current is reduced. If current is reduced, the losses will also be reduced, right? If the losses are reduced, we can say that the generated kVA is reduced. It will affect the fuel consumption, the life expectancy of the generator. As far as maintenance, also they will save a lot of money. The power company will save a lot of money. In return, the price per kilowatt hour of the power will be also cheaper. Now, let me give you an example. Calculate the value of capacitor in microfarad needed to improve the power factor of 5 kilowatt inductive load from 0.75 to 0.98 lagging. The supplied voltage is 220 Vrms, frequency 50 Hz. Okay? What is the commercial standard value of the commercial standard of the capacitor? So given P is 5,000, supply 220, power factor 0.75, convert it into theta, inverse cosine 0.75, we have 41.41. Also power factor 2, we need 0.98. Right? So theta 2 is inverse cosine 0.98. So we have 11.47. Determine the required C. So we apply the formula. C P tangent theta 1 minus tangent theta 2. So we have voltage is given in Vrms. So we can just replace 220 here. This is our theta 1. This is our theta 2. 2 pi F. This is the omega. So we already calculated 223 microfarad capacitor. So our working operation is 220 volts. So we will buy a capacitor is 220 microfarad, the nearest commercial power, commercially available capacitor, rated 220 volts, 50 Hertz because we have 50 Hertz. Okay? Now, let us try to consider this circuit this one is my load. I have resistor, 500 ohm, 150 nano. This is my load. Normally, because the power plant also has a capacitor. But first, let us try to determine whether it is an inductive load. The effect of this is inductive or a capacitive load. Right? We have a frequency. We can just also refer to the impedances. X of C is equal to 1 over omega C. So after calculation, X of C, I found it 424 angle minus 90. X of L, the reactance of this, the impedance of this inductor is 738. What's the formula? X of L is equal to omega L, right? Omega is 2 pi F. So what's your conclusion? We have X of L is greater than X of C. That means to say, this load is an inductive load. So this load is inductive. This is an inductive load because X of L is greater than X of C. And also, we can take now the total impedance. Total impedance will be equal to R plus JXLXC, and simplify rectangular and convert it into polar. We will have 590 with an angle of 32.13. How did I get 32.13? Arc tangent 314 over 500. 314 is the difference between XL minus XC. Right? Now, use a capacitor to improve the power factor to unity. So what are we going to do? First, we need to calculate the capacitor. But from the formula, we have here P. But what will be the P that I'm going to use? So P, from here I can calculate IRMS. IRMS will be equal to BG divided by set total, right? We have set total, we have BG, which is 10 BPP, and convert it in RMS, we will have IRMS, and R equivalent. What is the R equivalent for this circuit? Which is equal to 500 ohm, right? After calculation, I obtained 17.95 watts. Now, using this value in this equation, tangent theta 1, tangent theta 2 is unity, tangent theta 2 will become 0, right? This is 0. So, to summarize, to simplify, C is equal to 57 nanofarad. So, 57 nanofarad is the capacitor. Let's call it CX, that I'm going to put in parallel here before the load. So what will be the effect? Initially, we have here IG. The objective power factor correction is to reduce the current. So my conclusion here is the IG will be less than, IG prime is less than IG. So we reduce the current. How do we know that? Let's study the phasor. So from here, this is the voltage angle 0. This is the source. And by the way, why did I put here the I sub C on this phasor? Because the voltage across the capacitor is the current leading by 90 degrees. For the capacitor, the current is leading by 90 degrees, right? As you can see here, this capacitor is in parallel with the source. So this is my source, angle 0. I have here an angle of 90 degrees with respect to the source reference. And what happened? What will happen? This phasor will reduce this phasor. It's go up. You add it using phasor analysis. And then after that, you connect this one here. It will be reduced. Right? This will be subtracted from this one. From you can observe that the length IL is longer than I. So we can say that, and I here is I prime, IG prime. So we can say that we have reduced the current, the value of current. Okay, so there is a power factor correction there. So if there is reduced the current, what happened to the power? So initially we have IG. Let's say IG is equal to BG divided by the total impedance, right? So BR is equal to the you can analyze or you can measure it if you are in the lab or something. You can just measure it directly using oscilloscope, or this is equal to BR will be equal to the current I times R, right? Of course, we have to consider the phase angles. BL is also equal to uh, the current multiplied by X of L, and BC is the current multiplied by X of C. And theta is we already calculated the theta, it's 32 degrees, 32.13, I think, 32.13 degrees, right? So this is the initial condition when we did not put the capacitor. So what is the power? We can calculate the power. The power here is equal to, I can use P is equal to IRMS squared times R, right? And QC, we have an equation which I showed earlier in the previous slide, and also here QL, and S load is simply the BG times I total, which is also equal to the B load, SG. SG here is equal to, SG, you can calculate SG is equal to P squared plus QL minus QC squared, and you take the square root of that. This is equivalent to SG of the load, right? This is, sorry, SG of the load, this one. This is SG of the source. The power factor is the cosine of 32.13. Now, after I put the capacitor, let's analyze the circuit. After I put the capacitor, we have IG prime is equal to the vector IC plus the vector IL, right? IG prime. In this case here, at the top, IG is equal to IL, right? IG here is equal to IL, but here, IG is equal to vector IC plus IL, right? There is a difference. So, what happened? When we connect a capacitor, what do you observe? IL did not change, right? Why do you think IL did not change? It's because, if you look here, this voltage between these 2 points, the voltage is equal to VG, right? This is the voltage across the load. When we put a capacitor, the voltage between these two terminals is also equal to VG, so that means the source is not changed. We have the same value of IL, right? We have the same value of IL. So again, let's go back to the phasor. We have, this is the original IL, or I, and then after power factor relation, we have this I prime, because of X of C. Let's go back here, we have theta 2, right? Theta 2 after power factor relation. So again, what is IG nu? Let's say IG nu or IG prime. Question here is IG nu, it should be less than IG. So IG nu, I prime must be less than the I, right? I load. What do you think about I load? I load here, the current passing here, will not change because the voltage across this load is also the same. So it's the same. There is no change. What about I sub IC? IC is actually equal to BG over X sub C. You can calculate that, or otherwise you can do measurement in if you are working in the lab. You can do the measurement, how to measure the voltage here. If you don't have a current probe, just connect an oscilloscope. This is the source, and put a resistor here to that very small resistor, let's say 10 ohm. Get the voltage across the 10 ohm resistors and divide it by 10. You will have the current, almost the same current that you can obtain from here. If you want to get the IG, you just put a resistor here. If you don't have current probe, and measure the voltage across the 10 ohm and divide it by 10, you will get the current. Take note that when we talk about AC, we talk about magnitude and phase. Okay? So this is after we connect the capacitor. BR, what happened to the BR? So if this is the same, the current is same, the I load is the same current passing here, BR will also be same. Same also. This doesn't change. Also BL also same. And also BC also same. It did not change. What will now happen to the theta nu? Theta nu will be what? Will be very close to zero, right? Power factor will be zero. So again, now what will what can you say about the power here? The power here after providing the capacitor will be the same as the power on the original circuit. So, but QL is also the same. We did not change because from here we have the same voltage, the same. QC is also the same. That means the S load did not change. However, SG now is SG prime. We call it SG prime compared to the SG of the source. So this one is smaller. It should be smaller now compared to SG of the original circuit. And of course, the power factor is very, very close to equal to unity. Right? This is what will happen. Thank you very much.